Good morning, this is Raphael Mudge, and this is a PIC development crash course. In this video, we're going to talk about what is PIC, Position Independent Code. We're then going to talk about COF, which is my favorite intermediate file format for working with PIC. We'll then talk about some of the PIC writing rules, and we'll talk about how to debug PIC as well. And finally, at the end, because we're going to do everything here the manual way to start, you may feel like, I don't know if that's for me, that looks a little bit messy. We'll talk about some tools and frameworks that can make that a little bit easier for you. All right, let's get started. So what is PIC? Well, if you go to Google and type Position Independent Code, you may come across the systems programming definition, which is a relocatable library, a library that can happily exist anywhere in memory. But we're not talking about that kind of PIC. We're talking about shellcode. Back in the day, we used to fire exploits against vulnerable applications. And the stuff that the exploits ran had to be position independent code. It makes sense because we don't know anything about that process context or computing environment when we fire that exploit, right? And the job of that position independent code was to spawn a shell that we could interact with remotely to control the compromised system, hence the term shellcode. That is the kind of PIC we're talking about in this lecture. Now, we're going to be talking about PIC assuming you're interested in writing tradecraft, post-exploitation tools, or even post-exploitation agents. And I want to share a few reasons why PIC can be advantageous over DLLs. First, it's very small. It's as small as you're going to get anyways. The other thing I like about PIC is I know exactly what's going on with my program. With a memory-injected DLL, there's a lot of stuff baked in the static library and the initialization code that may provide some value add I don't want. For example, something that I found out about, surprised me, is sometimes that initialization code registers a vectored exception handler from our memory-injected DLL. And that's just what we need, another exception handler floating around indicating where our payload lives in memory. Fantastic. The other thing about PIC is I have more control over the content and structure of my code in memory. With a DLL, there's a lot of content indicators, right? Like the header and the different section headers. But with PIC, you don't have that. The other problem with DLLs, you can get rid of those content indicators, so that is manageable, but you are stuck with no structural flexibility. You're always going to have the code and data right next to each other in a contiguous region of memory. With PIC, you don't have that. You can mix your code and data together, you can have your code and data in disparate regions, or have code just everywhere, whatever you want to do. So with PIC, you just have full control, and that's pretty cool. Now, the disadvantages of PIC are also the reasons for its advantages. The advantage of PIC, full control, right? Because we're not taking advantage of anything that's being done for us. The disadvantage, we have to do everything ourselves. The bigger disadvantage of PIC, though, is it's error-prone to develop. And let me take you through what I mean by that. When I compile a program, what my compiler produces is not finished, okay? There's a lot of information my program may need to run successfully, and that could be things like a pointer to a function in the Win32 API. And that stuff needs to be provided to my program. And when we're writing PIC, we're giving up the help of a linker sometimes, and we're giving up the help of the operating system loader. And so if our program has things that are unknown in it, then it's going to crash. And so much of this course is going to be about drilling that idea into your head and showing you how to check your program for those unknown things and how to work around having unknown things in your program so that your PIC runs successfully. That is the entire lecture today. So how do we run PIC? I think this is just a helpful piece of information to know. This is a little bit of a shellcode runner. Here I'm allocating memory using read, write, execute permissions. and I'm copying my shellcode over to that memory, and then casting it as a function pointer and calling that function. In effect, what I'm doing is treating my blob of PIC like a function and saying starting at position 0, start executing. That's an example of a shellcode runner. Now let's talk about COFF. COFF is the Common Object File Format. It is the output of a C compiler. It's not executable by itself. And its main consumer is the rest of the build chain, like your linker. Let's talk about what's in COFF. COFF is that standard container from compiler output. It has your compiled code. It has your data, because your program is a mix of the logic and sometimes data, things like constants or strings. That's your data that's in line with your program, but sometimes lives separately of your code. There's also meta information to help with debugging. We're not going to worry about any of that today. But what we are going to worry about are these hints. So when I said your compiled program is something that's unfinished, that unfinished stuff is documented by a compiler as hints that your linker and operating system loader are meant to work with later. And those hints are called relocations. And what they are is the stuff that is unknown by your program but needs to become known before it can run without crashing. Now, it is the job of a linker to combine multiple COFF files into one program, and to resolve as many of those relocations as it can and provide the combined code, data, and unresolved relocations in a format that an operating system loader can consume. And that contract between the linker and the operating system loader, that format, those have names like PE or ELF. So that's kind of how all of that fits together. Let's talk a little bit about more specifics on COFF. Your code and data are organized into sections. The text section is your executable code. Our data are your read-only constants. That would be things like your strings. Data are your read-write global variables initialized to some value. And BSS is also read-write global variables, but these are the uninitialized ones, the ones that are set to 0 by default. The reason BSS and data are not together is that BSS is a space-saving hack. There's never any data in BSS. There's just a hint about how much memory should be allocated and set to 0 when your program is running. But really, logically, BSS and data are basically the same thing. Now, we already talked about relocations. Relocations are placeholders for resources that may exist elsewhere, but where they exist is unknown to your program at compile time. Now, some of those are resolved by the linker. And when I say resolved, what I mean is that hint, that relocation is acted on, and the information is provided to your compiled program, and now that hint is no longer valid, it's no longer needed. That's what I mean by resolving a relocation. So yeah, some are resolved by the linker. A great example of something the linker can resolve is if you've got a program with multiple files, and this module happens to call a function in this module, well, that's not known where that function exists relative to this one at compile time, but your linker can take care of that when it's merging everything together. So that's an example of a relocation that your linker can resolve. The linker can also resolve relocations for data that are a known offset or distance from your code. And this is especially true on 64-bit Intel architecture, thanks to something called indirect addressing. We're going to talk about that in a little bit. Some relocations have to be resolved by the operating system loader. An example would be a function pointer for something in the Win32 API. Our program and our linker can't know that stuff at compile time. It's got to be provided by the operating system loader or something standing in for it. Other types of relocations that may come up are relocations referencing the base location of your code in memory or one of your data sections. This comes up a lot in 32-bit programs because of something called direct addressing, which we'll talk about later. But even in a 64-bit program, a handful of base locations relocations can come up as well. And you want to be aware of that because if there's a relocation that's not resolved, when you turn your code into PIC, it's going to crash. So that's what we're trying to avoid. Here's a cheat sheet of helpful utilities for working with PIC. We're going to play with object dump here in a moment. Crystal Palace, my PIC linker, can do a lot of this stuff as well. But yeah, this is just meant to be a reference. We're going to demo that right now. All right, let's try some of this stuff out. So here we are in Windows 10. And this is the same Windows 10 environment I set up in an earlier video on Tradecraft Garden. So we've got Windows Subsystem for Linux going. Right here we've got Crystal Palace. And today we're going to work with Prezzo.c. Very simple C program that pops a message box that says Hello World. Later we're going to turn this into position independent code. But for now, let me just compile it into a COF and show you how to understand that COF file. So we're going to come over here and we're going to use minimal new for Windows to compile it. And we're going to do -c, prezzo.c, and I'm going to output it to prezzo.o. All right, let's go ahead and take a look at the disassembly of this program. We're going to just do object dump, -d is in dog, prezzo.o, and there's the disassembly. All right, very small program, very easy to kind of understand what's going on. I don't expect you to be an assembly guru. You don't need to be, but it is very helpful to be able to follow along and at least mentally map what a region of the assembly might be in your C code. So yeah, that's our disassembly of our prezzo.c program. Now let's go ahead and take a look at the relocations, and we can do that with object dump -r as in Raphael. And here you can see we have 3 relocations in our text section. We're not going to worry about P data or any other sections. We really don't care about any of that. But we see we have 3 relocations. Everything is in hex. Okay, so at position hex 11, so we've got E, F, 10, 11, we have a reference to our data. And what's our data? That's our strings, right? Our read-only strings and other contents. And what are we doing? Well, we're using the load effective address instruction to load the pointer to our data, so the actual address of it, into register R8. And we're doing this in preparation for a function call. So we're getting ready, we're preparing our arguments. So that is one of our relocations. The other one for our data is at hex 18. So if we come up here to 15, 16, 17, 18, you'll notice that that one is not all zeros. Why? Well, we are accessing our data, but we're accessing the data at offset 5 within our data. What could both of those be? Well, let's take a look at object dump -s as in snake. And here we can see a hex dump of the different sections in our COF file. And what is at position 0 of our data? Why, it's the string test terminated by the null terminator 0. And what is at position 5? Let's do this. 0, 1, 2, 3, 4, 5. Why, it is our hello world string with an exclamation point. Okay? So we're loading these 2 strings right here. That's what those relocations are. Now what about message box A? That's at hex 27, so 2, 4, 5, 6, 7. And you'll notice we only have 4 bytes there. Why? Well, that's because in a 64-bit program, we are dealing with indirect addressing. And I'll talk more about what that is in a moment when we're back in the slides, but this is not going to be the actual address of message box A. It is going to be a offset from this next instruction to a full pointer for that function. And that's just a quirk with 64-bit x64 programs. But either way, that relocation needs to get patched, right? And what's happening here is we're putting that information into the register RAX. And here you can see we are calling it, and you can see there's a helpful little star to say, hey, we're going to dereference that pointer that is in RAX and call whatever is at that location. We're going to call the address at that location. So that is our assembly. Now, you don't have to do this exercise yourself. Object dump will do it for you. So if you do object dump RD, that will actually disassemble the program with the relocations in line for you. And this is just really helpful to, at a glance, know what is going on with your program. So that stuff I find really helpful. So if you take anything from this demo, I want you to know about object dump Ds and disassemble, R as in show me the relocations, and RD to see them together. So that's a little bit of what's going on with a cough. All right, let's talk about those PIC writing rules, or why writing 64-bit PIC is better than writing 32-bit PIC. In a 64-bit program, we have the advantage of something called indirect addressing. And what that means is an instruction that is referencing data will often do so not by the full quad word 8-byte address, but instead by a 4-byte offset of where that data lives relative to the beginning of the next instruction. I'm being a little pedantic with that, but it's accurate at least, right? But yeah, that's indirect addressing because we're referencing our data as offsets from where our code lives. Now, the practical thing about this is if we know where something is relative to our code, even if we know that at link time, we can resolve that relocation. We can act on it. And what we get from this is things like local module function pointers work. Because when we compile a program, if we want to access a pointer or load the address of one of our functions, we can do that. That's no problem in a 64-bit context. And that's thanks to indirect addressing. For the PIC writing use case, a practical benefit of indirect addressing is we can do things like append our text section and our R data together at build time and resolve all the relocations between the two. And the practical effect of this is that we get strings again. Like we have strings from our position independent code. And in fact, if you use Crystal Palace, there's a command, make PIC64, in its linker script that will do just that. It will extract PIC from a cough file and append the R data section to it and give you access to strings. But that only works in a 64-bit context. You can also do this with the GNU linker script as well. So that's not a Crystal Palace thing. It's just a benefit of what's possible thanks to indirect addressing. Now, why can't we do this stuff in a 32-bit program? Well, we can't do it because there's no indirect addressing. I should say it's not really true. For things like our branching instructions, jumps and calls, yeah, we can refer to things by an offset. But for anything where we're working with data, the full address, the full 4-byte address is expected. And so what that means is there's going to be a lot of relocations for the base address of your code and memory in a 32-bit program, especially when you do things like try to even reference the address of a function in the same module. So that's a downside to 32-bit programs. My recommendation is if you don't need to write 32-bit PIC, don't. Or if you do, write 64-bit first and then make it work 32-bit later. Now here's some rules for writing PIC and being successful. And I can summarize this entire slide with 3 points. First, declare the entry point function at the top of your code file. It has to be the first thing in your program. So if you're to disassemble it and look at what's at position 0, it needs to be your entry point function. Second, avoid language features that generate relocations. Third, what was the third one? Oh, third, have a plan for bringing the things you need, things that would normally be in a statically linked C library, or finding the functionality you need at runtime without knowing anything. And that would be things like getting at the Win32 API. So that would be this entire slide. But let me just jump into a few specifics here. Don't use switch statements. You don't want to use switch statements because those generate something called a jump table. And a jump table is something that is a combination of code and a table of full addresses within your text section representing each of the blocks within your switch statement. Jump tables are not position independent code friendly because they require the full address of each of those labels. So they generate relocations within the R data section. They are not PIC friendly at all. So no switch statements. Beware of optimizations. You can turn them on, but be aware that your optimizations may turn if, else, if, else statements into jump tables, not position independent code friendly at all. Or optimizations may reorder your functions, and that can be very frustrating if your entry point is no longer at position 0. The other thing I want to point out is in a PIC context, I like to assume I'm working in read execute memory. And in that context, you don't have global variables. You just don't. So not without like some sort of crazy hack. So be aware of that. You also don't have access to strings because strings live in that separate section, the R data section. I already talked about a way you can get strings back in a 64-bit context only, but if you're trying to be portable between 32 and 64-bit, well, you don't have strings in the way you're used to working with them. You also don't have the C standard library, and you don't have access to the Win32 API in the way you're used to working with it either. So these are the things to know, right? This is stuff that if you try to use it like normal is going to be unknown information, meaning your PIC is going to crash. Now, the other thing you need to be aware of when writing PIC are what I call sneaky function calls. Sneaky function calls are function calls generated by your compiler that you may not have intended or want. These are things that generate a relocation, and if they're there, your program is going to crash. Things like if you're using structured exception handlers. You might have a reference to this C-specific handler function, and if it's not there in your program is going to crash. Stack cookies, which are something your compiler will bake in as it sees fit as a security feature to guard against buffer overflows. If that function isn't in your program, and it won't be, that call is going to be a relocation and your program is going to crash when that's called. Now, another thing where we kind of do ourselves in a little bit is trying to use the stack like a heap and declaring a lot of stuff on the stack. Once you start getting over, say, a page of memory, Microsoft's compiler likes to put in a check stack function. And that's a relocation. It's unknown information. And when your PIC tries to call it because it's not resolved, your program's going to crash. So this is not exhaustive, but I want you to be aware that your language features and your compiler security features can sneak this stuff in on you. And if it's there and you don't do something about it, your program is going to crash. Now, what are some workarounds for all this stuff? Well, you can tame your compiler. You can use different flags at build time to turn off these language features. You can turn off jump tables. You can turn off structured exception handlers. You can turn off function reordering. One thing I find helpful If you want to use optimizations and you find there's one function that really breaks and you can't do anything about it, well, you can turn off optimizations for that specific function. You can do that with the optimize O as an orangutan 0 attribute. Now, all the stuff I'm showing here is for GCC because that's my preferred development environment. But I'm certain the Microsoft compiler happens to have similar flags and options as well. They're going to be different syntax, but the same stuff is there. Now, if you want to use strings, I already talked about, again, a way to do that in a 64-bit context, but the most universal way to have strings, again, is use something called a stack string. And what that is you declare a character array as a local variable and just populate it one character at a time with the null terminator in there. If you use this syntax, your compiler will generate move instructions that put this stuff on the stack, giving you a stack string. Now, what about not having a C standard library? Well, you can make your own. Just build a header file that has all the functions you need and include it into your PIC program. That's an option. The other thing I've seen some folks do is access MSV CRT, which is the Microsoft Visual C runtime. It's a library. You can access it via Win32 API, and that happens to have the normal stuff you'd expect to see in a standard C library. And a lot of people like to reference that and use that to make up for the stuff that's not statically linked into their PIC. I'm not a fan of it because it's too much of a hooking target for me. I would prefer to just bring my own functionality with me, but that's something you can do too. Now, what about compiler intrinsics? Now, you got to remember, we're not writing a regular expression engine as PIC. We're not writing the next great text adventure, right? We're moving bits and bytes around largely. And so my two favorite compiler intrinsics are stowsb and movesb. And what a compiler intrinsic is, it looks like a function, but it actually just translates to a CPU instruction directly. And so stowsb I think of as store byte string, but it's basically memset. And movesb I think of as move byte string, that's memcopy. So those are two compiler intrinsics I get a lot of value out of. There's certainly going to be others. Sometimes they're specific to your compiler, but you can get pretty far with just those as well. Now, what about the Win32 API? If we try to use the Win32 API like normal, we're going to have an unresolved relocation. That's a big problem. So here's the typical way we resolve the Win32 API. The typical way is to bring in some code that will find the process environment block and walk the list of modules currently loaded in the process, look for kernel 32, parse that DLL in memory, look for its export address table, and find get proc address and load library A. And those are our bootstrapping functions. And then once we have them, we use those functions to resolve everything else. So that is the most common way. It's not the only option you have. One of my favorite options is, if I know those values beforehand, to just patch them in and provide them to my PIC. One thing to know about this behavior of walking the export address table of kernel 32 is that there are behavior detections around that are very robust. And if you care about that, that's gonna get you burned. So be aware of that. But it's also the most common way. It's what we're gonna use here. And it is a very robust way to find the Win32 API starting from nothing. Okay, now we get the real fun. We are going to turn this C program into position-independent code. And warning, we are going to do this the messy copy and paste way, and that's because I just want you to see what's going on. So what we need to do to make this working position-independent code is we need to resolve all of those relocations, right? We need to get rid of these relocations, and we need to have an entry point at the top of the program. So let's do that entry point first. Let's do void go. We'll have it call the rest of our program, the bottom. Let me create a function prototype up here so our compiler doesn't complain. And this is just me. I like to have my entry point function at the bottom. I structure my C programs so everything is in reverse order, basically. So yeah, we've got a rest of program here, and go is at the top. Cool. Now let's work on the Win32 API part, because we don't want that relocation from message box. We don't have a loader. So we need to actually bootstrap that pointer somehow. So for that, we're going to go over to the Tradecraft Garden. That's my collection of example position independent code projects, largely focused on being DLL and COF loaders. And we're going to go to simple loader 1, and we're going to look at loader.c. And what loader.c does is it declares a local variable funcs and calls find needed functions to bootstrap the functions we need. So we're going to bring that over into our program. Okay. I don't like these green things, so I'd like to get rid of them. All right, so we need to get find needed funcs and the definition of funcs into our program as well. So let's go ahead and copy and paste that out of our loader. And if we come up here, here's our Win32 func struct that has function pointers for load library A, get proc address, and virtual alloc. And here's find needed funcs. What it does is calls functions to find our kernel 32 module and to walk that, looking for our bootstrap pointers by a pre-calculated hash of the string. So of their string name. So let's go ahead and grab that. Oops. I'll just bring that into our program. I'll get rid of these comments just to make it look a little bit cleaner. We don't really care about virtual alloc, but I'm not going to get rid of it. We don't need it here. All right, so that's that stuff. Now we need find function by hash and find module by hash. And in my Tradecraft Garden projects, those are actually in a refactored version of Stephen Fewer's reflective loader. And that's split amongst these three headers, loader.defs.h, loader.h, and resolve eat.h. So we're going to bring that in. If you're using a source code framework, that functionality is going to be hidden from you in a header too. Like you're always going to have some means to bootstrap the Win32 API because that is a part of a position independent code project. Okay, and loader.defs.h loads windows.h, so we don't need that anymore. So those are our definitions. And real quick, I'm just going to make sure this compiles. So let's come back over here. And let's do gcc-c prezo.c, prezo.o. Oh, I forgot to copy the header files over, so let's do that real quick. So we're going to pull these out of the Tradecraft Garden, just going to copy them all over. And you'll see loader.h, loader.defs, resolve eat.h. Let's recompile it now. Fingers crossed. All right, that worked. Good. We're not done though, right? Like we've got our function pointers we need, but we don't have a message box A. So we have the bootstrap function pointers. So let's go ahead and set that up. So what we're going to do is we're going to use the Win32 func macro to declare a function pointer for message box A. And I don't like magic, so let me just explain what's going on. There's a macro up here that's using the type of macro that's built in to give us the type of our message box A function and declare it as a pointer named message box A. So that's what's going on there. All right, let's go ahead and use our bootstrap functions to load it. So we're going to do, let's see, handle huser32. User32 is the library with message box A, and we're going to do funcs.loadLibraryA. And we're going to load user32. And we're going to do message box A. The function pointer is equal to funcs.getProcAddress. Handle user32A, the library, and then the function name, message box A. Got to make sure you spell that right, or that becomes something you get to track down. All right, that looks good to me. User32, message box A. And, oh yeah, I'm thinking, is there something I'm missing? So yeah, what we want to do is, just to keep the compiler happy, we want to cast the output of getProcAddress to the type of message box A. That should work. All right, let's go ahead and compile this. Good. Now earlier, when we ran object_dump-r, we had these 3 relocations, right? Like including the one for message box A. Let's do object_dump-r again. And again, we don't care about the p-data section, but you're going to see our message box A relocation is gone. Yay. But what we have now is 4 our data relocations. Why? Why do we have those? Well, because we used strings, right? Like we have user32, message box A, hello world, and test. And if we are to object copy this out of our cough file, just dump the text section to a file, those relocations aren't going to be resolved. Our program is going to crash. So what do? We use stack strings. So let me go ahead and bring those in. We're going to use string user32. I want to emphasize again, this isn't the only way, right? We could use a C++ const expression to create a stack string. Like there are different ways to do this, but the most universal one is what we're doing right now. And I'm going to just copy and paste these other ones because you don't need to see me type all of that. But these are stack strings. Now let's go ahead and just fill these in. And we're going to do string test. Looks good to me. Hopefully I didn't make any typos. That's what I'm looking at right now. What you should know is this is not my first time recording these demos. I've gone through a couple iterations. And every time I did this in some way, I made a mistake that surprised me. And that's what I mean. When doing things kind of without tooling support, this can be very, without tooling or a framework, this can get very error prone. But this looks good to me, so let's do message box A. Again, I'm paranoid. I'm like triple checking. All right, let's compile this and see if it works. Compiles. Let's look at the relocations and ignore p-data, but you see no relocations in our text section. Go us. We have successfully converted our PIC to, or excuse me, our program, our message box A program, to position independent code. A little bit messier looking now, right? Yeah. All right, let's go ahead and try to run it. So we're going to come over here and we're going to use the run.x64 program that comes with Crystal Palace. And this is a shellcode runner. It does what I showed you earlier in the presentation, except it loads the shellcode from a file and it passes execution to it. So we're going to give it, well, we got to actually extract our shellcode first, so let's do that. So we've got prezo.o, and give me a second, I'm actually going to go find the slide with the different commands for our reference. And we're going to use object copy to extract the text section from our cough, because that text section with no relocations is, in theory, our ready to run position independent code. So let's do this. Let's do x86, 64, W64. By the way, in my development environment that I work with, I have aliases for all this stuff. I do not type the Ming W stuff every single time. That's really, really tedious. So I recommend creating aliases for this stuff if you can. We're going to do a dump section, and we're going to dump the text section to out.bin, and we're going to get that from preso.o. So that's object copy. So without any other tooling or support, that's how we export position independent code from a COF, or export the text section anyways. All right, let's try to run it. So we're going to go up, tcg, preso, out.bin. And all we got to do is press enter to continue. We were supposed to get a message box. We didn't. I actually know why, because I've left out a very important detail, and it's not something that's related to PIC, it's related to the code that we copied and pasted. There is a reason that is very obscure. That is the reason our PIC is not working, and the reason that we are not getting hello world. It's not something I'd expect you to know. Again, it has to do with the code we pulled from. So what we're going to do is, after we talk about debugging, I'm going to show you how to track down where in our PIC a crash is occurring and cross-reference that back to which function, so we can go in, troubleshoot, and resolve it and get something working. All right, let's talk about some PIC debugging survival skills. One option, write your capability in C and then port it to PIC later. You can do that. I don't mind writing things as PIC now, just directly, but you can start with just making something a normal executable and making it PIC, just to have access to working with it the way you're used to. I'm going to show you in a moment how to do printf debugging from PIC. My favorite way to do that is to use a Win32 API called output debug string, and to wrap it in a function that gives me access to format strings. So I can do things like pretty printing strings and pointers and things like that. Any output past output debug string is going to be viewable either in a debugger or through a tool from sysinternals called debug view. And the printf debugger wrapper function we have does exist in the Tradecraft Garden with Simple Loader 3, and so I'm going to show you that in a moment. And I'm also going to show you how to debug the crash we just experienced in that last demo. And I want you just to have the confidence that if something mysterious is happening, that you're empowered to try to figure out where that mysterious behavior is coming from in your PIC program. One thing I'm not going to demo, but I think is important, is the concept of using the int3 intrinsic. And what that does is generate the debug break instruction. So when a debug break instruction is in a program, what will happen is once it gets hit, the program will immediately pause, and if debugger is attached, you'll have the chance to poke around at the context from that place. So that can be a great place to something you can insert in your program to just force a pause right before something bad is known to happen, so you can just step through and watch instruction by instruction what's happening. So that's the int3 compiler intrinsic. I find that very helpful too. All right, we're back. So let's go ahead and debug our PIC. You'll recall when we last did this demo, it crashed, right? Well, let's figure out why. So when we run our PIC with run.x64, it says, please press enter to continue. Why? Well, this is an invitation to attach a debugger if you want to. So when you press enter, and if it crashes, you can see why. So we're going to go ahead and attach a debugger right now. And I'm using x64 debug. And I'm just going to go to File, Attach, and double click on Run. That's our shellcode runner. Press the little run arrow. That's right here. And now our program is running, waiting for us to press enter. So let's come over here. Watch the magic happen. Let's press enter. And we've got an exception. Uh-oh, we tried to do something with a bad memory address. Oh no, that happens, right? Let's see if we can figure out where in our PIC that is occurring. So let's come over here and let's go to the log. And the first thing to look at is the exception address itself, all right? And what we want to do is try to figure out if this is occurring somewhere in our PIC and where, or if it's occurring somewhere on the somewhere else. If this is not our PIC, if this is deeper into a Win32 API, what we want to do then is start looking at the return addresses on the stack and following them in the disassembler, looking for something that could be our PIC. But the main thing is we want to find what we think is our PIC and cross-reference where the program is currently at with our disassembled PIC. So we have a better chance of knowing where the crash occurred. So let's come over here. Let's go back to the exception address. And you can see the exception here as at offset 628. And we're going to assume this is actually our PIC. So let's come over here and let's disassemble our PIC. We're going to use object dump RD. R won't really do anything because there should be no relocations. But what's great about D is we have the function symbols. We can see what's being called with the different call instructions if it's something local. And this is very helpful for figuring out where in our C code an issue may be occurring. So what was our offset? 628, right? That's the exception address. Let's go find 628. We can see 628 happens to be in find module by hash. That's not code you wrote. That's not code we worked on for this demo. That's something we copied and pasted from Tradecraft Garden. So let's go look at find module by hash, just eyeball it and see if we can figure out what maybe could have gone wrong. So let's go back to the garden, simple loader 1, and we're going to look at resolve eat.h because that's where find module by hash is. Now what I want you to see right away is this code has to get the process environment block, right? But how does it populate the variable? Well, if you're in a 64-bit program, as defined by WinX64, it does one thing. And if you're in a 32-bit program, and it knows if WinX86 is defined, it does another. And if neither are defined, it doesn't populate that variable at all. So this right away is a clue that we are missing when we're compiling the program a definition we need for this function to succeed. So we need to define WinX64. So I think this is a great example of just a very obscure kind of crash you might come across and how to pinpoint where it happened in the code and just investigate and say, that's maybe something that went wrong. So let's go ahead and close the debugger. And we're going to go ahead and recompile our program, but we're going to define WinX64. And we're going to do object copy to extract the text section again. And now let's go ahead and run it. Press enter. Hello world. So there we go. What's fun about that, by the way, when I first did this demo, like as a practice, I actually ran into that issue and I didn't know what it was and I had to like debug through it. And I've chosen to kind of recreate that here because I think it's a great example of showing you that you are empowered. If you can find where your PIC is in memory and where it last executed in the debugger, you can disassemble it locally with all that symbol information and figure out where in your C code that error likely occurred. And that's usually enough to track down the issue or get close to it. Now, my other favorite tool for debugging that I consider really important is printf debugging. Make fun of me or call me what you want, but that's how I do things most of the time. So let me show you how to do that in PIC. So we're going to go to Tradecraft Garden again. And we're going to go to simple loader 3, resource masking, and we're going to go to debug.h. This is my implementation of dprintf, which is a wrapper for output debug string, but lets us pass format strings so we can pretty print strings and pointers and things like that. And this is a position independent code, so it's position independent code friendly. So we're going to copy this over to, we're going to copy the header over to our project. So let's go ahead and grab that. So let's copy up, simple RDL, was it mask, source, debug.h. And we're going to bring that into our program. Okay. Include debug.h. All right, let me show you a little bit about how to use it. We're going to add some debug messages over here. So this is the prototype for dprintf. Import funcs, by the way, is win32 funcs with one less value. So we need to cast win32 funcs to that to use dprintf. So we're going to do dprintf import funcs star ampersand funcs, and we need to give it a message. And we're just going to use a stack string here. So we're going to do char star debug, and we're just going to give it maybe %p 0. So we're just going to print pointers out. That's all we're going to do with this. So we're going to do string debug. And let's give it some pointers. We'll give it handle user 32 and message box A. And the reason I'm showing you this again is just to let you know that you're empowered. When you're writing position independent code this way, you can do printf debugging. If you see it crash, you don't know where it's going, you can cross-reference that and try to figure out where in your PIC that crash may be occurring. So that is the message. You're empowered. All right, so these are our dprintf lines to get these pointers out. Let's go ahead and compile our program again. And just a good thing to do, a good habit to get into is, let's just check the relocations. Oh, excuse me, let's do -r. All right, no relocations in the text section, good. It's always good just to make sure we didn't introduce relocations accidentally. And remember, your compiler can do that too, so just a good thing to check. All right, let's do object copy to export our text section. So we have our position independent code. Let's come over here to the first tab and let's run that. And to view the debug output, the output debug string, or dprintf, we're going to open up debug view, which comes with sysinternals. So let's go ahead and do that. Make that smaller, press enter. There we go. Hello world, our program worked, and there's our module for user 32, and there's our message box A pointer. So that's an example of debug, printf debugging, yeah. All right, let's talk about some options to make all of this easier. First, you can use a PIC template. And what you get with a PIC template is a set of working build files that have already been thought out, and the compiler has already been tamed for you. One of the ones that has gained a lot of traction within the researchers I follow is Stardust. And that's a PIC template developed by Paul Unger, better known as Cracked Spider. And it's a source code framework, and it helps you with Win32 API resolution. It gives you printf debugging. The way it gives you back PIC is everything compiles, I think, into an executable, and it carves it out with carves out the text section with object copy. One of the things I thought was really clever in Paul's source code framework is how he does strings. Now, he's figured out a way using C++ templates, which are black magic to me, to be frank. But he's using C++ templates and some magic with linker script, the GNU linker script, to know the section offsets for even a 32-bit program. And he's using that to give you a function that lets you just pass a string constant and get the correct address for it in memory. And as far as I can tell from reading the source code, that works 32-bit and 64-bit. I haven't seen that before. I thought that was really cool. And so that's something that's in Stardust that's pretty novel. If you want to look at the project, you can check it out on GitHub. The other thing I really recommend, go check out Paul's blog post, Modern Shellcode Implant Design. And in that blog post, he advocates why he thinks using position-independent code for agents is interesting, and talks about some of the tricks that made its way into the current incarnation of Stardust. So that blog post is very much worth a read as well. Another way you can write PIC is to pair a tiny loader with a COF file. And that's exactly what I did when I came up with beacon object files. So a little bit of history on that, which I wrote about in a blog post pretty recently, is back in 2019, I was looking at PIC as an alternative to using fork and run for post-exploitation tools external to Cobalt Strike's beacon payload. And I wrote a source code framework, and I ported a lot of capability over to it, and I became very frustrated with it because what I had wasn't very good. And I was trying to find something I could expose to users, and through a happy accident, I arrived at the idea of processing a COF file, extracting the relocations, and resolving them within my C2 agent, and basically getting executable COFs. What's really nice about pairing a COF file with a loader is you get access to strings again in a 32-bit and 64-bit context. You as a programmer don't have to worry about it. You have read-write global variables. You have access to function pointers again for things within your local module. And you have easy access, or I should say ergonomic access to the Win32 API. And that's through something I call dynamic function resolution. And that's a convention where you specify the library, $, the function name, and the loader that's processing your beacon object file takes care of that for you. So I consider that PIC. When I came up with beacon object files, they were very much an alternative to writing position-independent code. The difference is instead of including everything in a source code framework, you just have the loader as something that's separate from your COF, your executable COF. Now, one bonus to doing things this way is that your loader can also check for unresolved relocations and warn you or do something else instead of running the program that's destined to crash. I'm such a fan of this loaded COF concept, I created Crystal Palace. This is my open source position-independent code linker project. Now, when I think of a linker, again, I think of something that takes multiple object files, merges them together, and then packages that into a format ready to be consumed by an operating system loader. That's not what Crystal Palace does, not at all. It doesn't merge files either. What it does is it appends them one after the other in a way that you specify in a specification file. And the specification files are Crystal Palace's linker script. What's nice about that linker script is you can specify how those files are encoded. You can encrypt them, you can encode them, you can obfuscate them. There's a lot of different tools to do that. The other handy thing Crystal Palace does is it lets you reference files appended to a position-independent code as symbols within that position-independent code. So it gives you a way to just access one or more things that have been appended very easily. The other thing Crystal Palace supports are PICOs. And PICOs are very similar to Cobalt Strike's beacon object files. They have a Go entry point, you have dynamic function resolution, and the same types of relocations are taken care of, giving you global variables, strings, and everything else. So you can think of PICOs as basically being beacon object files, but without the beacon API. I am a big fan of this loaded COF thing because it's so much easier to work with than just writing everything as straight PIC. The other thing Crystal Palace provides is link time optimization. And what that feature does is it goes through a file and looks at any functions that aren't used, either called or referenced, and it gets rid of them. So if you happen to have a big header file, that's your little mini C runtime, that you're using between projects and capabilities, the link time optimizer is a way to cut out anything that you're not using to keep your PIC as small as possible. The other thing Crystal Palace does is code mutation, and this is really cool. It will disassemble your program, rewrite individual instructions, and put it all back together, giving you something that has variation each time you build the project. The other thing I like about Crystal Palace is because it's aware that you're using it for position-independent code, it will warn you about anything it detects as a potential error that it thinks will make your program crash. So if there's an unresolved relocation, it's going to tell you. The other thing it'll do is if you use the function entry point named go, and that's not the first function in your PIC, it'll warn you about that too. So it's a very handy piece of assistance to have as you're building these kinds of projects. Now you can use Crystal Palace as an alternative to object copy and object dump. Okay, so you can use it just to say I've got a program and I want to assemble the parts together using a specification file. But my bigger goal with Crystal Palace is to provide a path to separate offensive security tooling capability from tradecraft. And when I say tradecraft, I mean load and runtime evasion tradecraft. And so a lot of the APIs and the CLI tools for Crystal Palace are designed around pairing your position-independent code project with some capability. And that capability can be a memory-injected DLL or a capability written as a memory-injected COF, or a memory-injected PICO, I should say. Now, why would I want to do this? Well, I maintained one of the most popular red team command control frameworks for about a decade. And if I understand anything, I understand the long-term maintenance headaches that come up with maintaining that kind of capability. And one of the most painful things is when tradecraft happens to be mixed into the code of the capability itself, or worse, when the loader requires cooperation of the capability for tradecraft to work. It's not maintainable, and it makes it very difficult to add new things. And a lot of care has to be taken to make that stable. So with Crystal Palace, I am showing you how to actually write tradecraft and do all the things you would see an advanced C2 do, but to do so completely separate of any specific C2 and in a way that is actually agnostic to even the C2 use case. That's what I'm building. That's what I'm showing you the path on. Now, why do I care about this? This is not really a technical project as much as it is a social effort. My message is this. I want to containerize tradecraft, load and runtime evasion tradecraft, as something completely agnostic to a use case, because at that point, it's not malicious software. It is security ground truth. And why does that framing matter? Well, it matters because if you're a security researcher and your work is visible enough, the threat intelligence community and the vendors they work for will seek to make your life hell. And they will attack your reputation, and they will throw shade at you, and they will do everything they can to position themselves as the security saviors defending the world against the harm you have brought into the space. And what I'm doing by containerizing security research as security ground truth is trying to carve out space for security researchers to publish code publicly or sell privately. That should be your choice, in my opinion. But to publish code privately or publicly if they want to, and to participate in the security discourse. All right, and I'm really working towards a win-win situation, something that's containerized, easier to maintain, and is itself a standalone unit of study, but can work with all of the red teaming tools too. And I think that that is also actually very important. So that is kind of the mission and path I'm on with this. That's why I'm doing this work. Now here's the assumed architecture of Crystal Palace. Again, you can just assemble a PIC project. I'm going to demo that in a moment. But the broader assumed architecture is this. You have a PIC bootstrapper, and appended to that, you have one or more PICOs that actually do the load and runtime evasion. You can do some of that in the PIC bootstrapper as well. But the end thing that gets run is the capability. And again, that can be a memory-injected DLL or a memory-injected COF. I support memory-injected COF this way because you get all the benefits of PIC. It's small, you know what's in it, and you can dictate how it lives in memory. And you also get the benefit of link time optimization, code mutation, if your end capability is a COF as well. So that's a pretty powerful and attractive combination. So with this architecture, yeah, you have these supporting COFs that implement the tradecraft. And the other thing that's really nice is as your project is loaded and settled, you can start deleting the pieces you don't need, which I think is better for the longevity of your capability as well, if that's something you care about. All right, last demo. I'm going to show you Crystal Palace. I just want to demo Crystal Palace as a PIC assembly tool here. We're not going to talk about the tradecraft and capability stuff. That's what Tradecraft Garden is for. But I am going to show you how to get some value out of Crystal Palace for a project like what we're doing here. So first thing we're going to do is we're going to create a Crystal Palace spec file. So let's open up prezo.spec. We're going to create a 64-bit target. We're going to load prezo.o. And we're going to tell Crystal Palace we want to use it as 64-bit position independent code. And remember, that marries our text section and our R data together. So in a 64-bit context, we have access to strings again. All right. Now, the other thing Crystal Palace can do that I think is really cool is link time optimization, right? So we're going to turn that on with optimize. And one of the challenges, though, when you start mutating or optimizing your code is it becomes harder to debug. All that cross-referencing stuff I just showed you no longer applies, right? Because your program is now a mystery to you. Well, I thought about you, and Crystal Palace has a command, disassemble, to actually take our PIC that has been optimized, disassemble it with any relocations and symbols it knows about in line, and dump that to a text file as part of the build process. So that is what the disassemble command does, and that's what it's for. And we're going to use export to export that to an array of bytes, and that is our spec file. Very simple one. And let's just bring some value over here. So what I'm going to do, because we can now, because we've got our text section and our data put together, I'm going to get rid of these stack strings and just use normal strings. So user 32, message box A. I just want to demonstrate that, like we get some sanity back. And for we can do debug, so huser32 is %p, so we can actually have some proper contextualized printf debugging, right? Message box A is %p. Line those up. And let's get our hello world string in there. We'll just say hello world from PIC. All right. So there we go. Modified that a little bit. Let's go ahead and build that real quick. So we're going to compile it. Let's not forget the dwinx64. That can become a problem, right? And let's go ahead and try piclink. So piclink is a Crystal Palace command And what it does is runs a spec file with whatever target you specify and assembles a final PIC for you. So we're going to do PIC link up tcg prezo.spec 64. And we're going to dump that to out.bin. Press enter. It's going to take a moment because we've got a Java jar file, which is a zip file, and the disassembly to do the link time optimization requires a lot of constants that are buried deep in that zip file. All right, so we've done PIC link. We've got our out.bin. Now let's go ahead and demo run.x64.exe out.bin. First thing I want you to notice, when we were running everything before, with the dprintf even, we had 3,000 bytes. So by just using optimize, we got our position independent code down to 1.5 kilobytes. Why is that? Well, when we included all those things from Tradecraft Garden, we included a full DLL loader. We only need some of it, and we only need some of it for the purpose of walking the export address table. But yeah, we don't need all of it. So the link time optimizer got rid of the stuff we didn't need. So that's why our shellcode is smaller. All right, let's come over here to debug view, press Control X to clear it, press enter. There we go, hello world from PIC, right? And you can see our debug messages, so everything worked. And just to show you what our disassembled stuff looks like, it's very similar to what you would expect to see from object dump. You've got all the symbols, and the program is broken up by function. And so that can aid your debugging as well. So that is a Crystal Palace specifically just as a PIC assembly tool. All right, in this presentation, I took you through what is PIC, Position Independent Code, and we talked about COFs, my favorite intermediate file format for working with PIC. We talked about the PIC writing rules and the pitfalls, and again, if I could summarize that in 3 ways, make sure you have the entry point at the top of your program. It has to be at position 0. Make sure there are no unresolved relocations in your PIC. If there are unresolved locations, your program is going to crash, and have some sort of plan to either bring the functionality you need or to bootstrap it and use the Win32 API. That is the PIC writing rules in a nutshell. I showed you some PIC debugging survival skills, and we talked about some things that can make your life a lot easier. Specifically, I pointed you at Stardust, and I talked about COF, and I talked about Crystal Palace. Now, I want to close this out with just a few resources that I found really interesting, and if you're interested in this, you may find them interesting too. When I started working with PIC in 2019 for the post-exploitation tool use case, I went to Matt Graber's Writing Optimized Windows Shellcode in C blog post. I think that's still worth a read today. Also, Shellcode, a Windows PIC blah, blah, blah by ModXP from 2016 is a really great survey of different tricks for writing position independent code and the history of them and different projects over time. So I recommend checking that out. One caveat for both of those blog posts, neither of them are live at their original site anymore, so you will need to use web.archive.org to access them. The other one I found really interesting too is a PIC library by Silent Warble, and that is, it's on GitHub, but really it's just a bunch of links to different PIC related templates and projects that you might find really useful. And Silent Warble is the author of Hannibal, which is a post-exploitation agent for Mythic, written as position-independent code on Paul Unger's Stardust framework. And so that work is what kind of signaled to me, okay, wow, yep, all of you are getting really serious about moving to PIC. That's cool. So go check out those resources. It's a fantastic collection. I hope you've enjoyed this information. I certainly put it together in the spirit of taking what I know and trying to share that with you, because to me, that is what being a hacker and being a security professional is all about. And so again, I hope you enjoyed this. Good luck and happy hacking.